Okay, chapter 2 starts us on derivatives here, and there's a really good explanation of instantaneous rate of change, okay, to get us started here. But I want to focus on chapter 2, and just a quick reminder that we're going to start on 2.1 today, the derivative function. And if you want to review materials, the Unit 2 materials, the PDF lessons are in this area right in here. Okay, so let's get into chapter 2. And the following example between instantaneous rate of change and average rate of change. So imagine that a driver's speeding down the highway at 140 kilometers per hour. So he's speeding. Here's police siren, and police pulls him over, okay, and charges him with speeding. The driver's argument, okay, is that he wasn't speeding because he traveled, 200 kilometers in 2 hours. So that's an average speed of 100 kilometers per hour. Okay, his home was 200 kilometers away, and it took him 2 hours. But the speed, the speed that was registered at a particular instant was 140. Right, there's the instantaneous rate of speed, instantaneous rate of change. That's speed. That's what the driver. That's what the police officer catches him at just at that instance. Okay, and that's very different from average rate of speed. Okay, or average rate of change. Okay, so calculus. Okay, we in chapter 1 we worked on the building blocks of calculus, and we're going to get into more specific rate of change, and thing called derivatives here in this particular unit here. So our learning goals and our success criteria are here. We're going to understand and determine derivatives. Okay, understand what this concept of a derivative. Realize that some functions just aren't differentiable. Rules for determining derivatives. Okay, composition of two functions. Okay, and problem solving with instantaneous rate of change or derivative type problems. And these learning goals will lead us to our success criteria and doing all of these things, understanding exactly just how they work. Okay, so let's get into talking about a concept of a derivative here. Derivative is a word that you're probably familiar with or might be quite common to you. Derivative is an adjective. It can be used to describe something that's related to or linked, connected. So some examples here: Darwin's work is derivative of moral philosophers, equity-based derivative products. These are things maybe you've heard derivative as an adjective used in these types of expressions here. Derivative can also be a noun. Okay, a noun is something that's closely a derivative as a noun is describes something that's closely based on or similar from another source. Okay, it's the root, the same, or another language, an arrangement or product whose value derives from or is dependent on the value of an underlying asset, such as a commodity or currency. Okay, it represents a rate of change of a function in math. Okay, so our derivative function is a rate of change function. Okay, so some examples here. Okay, when I use derivative as a noun. Okay, so it can describe. Okay, some of these common terms. Now I do this. I don't often do this with math classes. Talk about the origin of a word. Certainly, but I think it's important that we distinguish with derivatives here. Derivatives are the basis of calculus, and I think it's important that we talk about derivatives as a noun, right? It can be, an official function, right? So something that can be calculated. Okay, a noun, a real thing. It can also be an adjective, okay, that describes an action. Okay, so a rate of change in some ways, as a slope can be an action, describes what's happening on a function. So if we talk about a derivative as a function that has a rate of change relationship, I think we can see the difference between a noun and an adjective pretty clearly in that case. Okay, so our derivative function is something we have been working on. Okay, there was a previous question or two back in chapter 1 where we had to evaluate this limit as h approaches 0, of my difference quotient or difference limit here. Okay, so where I was taking the slope and finding it. And now from this point on, I'm going to call this my derivative. Okay, and I use the notation f prime at x, or f with a little tick, like it's almost like a 1. Okay, but it's on your keyboard. It's the apostrophe key. So we call it f prime at x. Okay, and that's a derivative. Okay, now we know the derivative is the slope of the tangent line at a particular point, and it's also the instantaneous rate of change, at a particular point here. Okay, but this is how we're going to start talking about this special function that describes the rate of change, the instantaneous rate of change. It's going to be f prime. Now there are lots of ways we can use notation to describe derivatives here. Lagrange used notation y prime or f prime, okay? That's the most common one that we'll see. In this class, we'll often see Leibniz notation. That's dy dx for derivative, okay? Or d at f at x over d at x. And I can also say, okay, when I evaluate a function, I can say f prime at a, okay, or dy dx when x equals a, okay? And that's when I evaluate a function. So not only am I going to be able to find the derivative equation of a function, right? Okay, and these derivatives, okay, this little process right here is going to lead us to, okay, a derivative equation, right? An equation that describes the derivative. But I can also, if I have an equation, I can also evaluate it, okay, at particular spots here. So think about what's going to happen here. If this derivative function is a rate of change, okay, of the tangent line, okay, I'll be able to find an equation, right, a derivative equation that represents a function that describes the rate of change. Okay, and not only that, I'll be able to evaluate it at any point and find actual values of slopes of those tangent lines at any point along here. Okay, so again, here is our derivative function. We've been doing this, okay? We did this in the last chapter a couple of times, okay? And we're going to start on working on this right now here. So finding a derivative or differentiation is the process of finding a derivative of a given function. First principles, okay, is the process of figuring out or computing this limit, this following limit. Okay, so I'm going to find, okay, the derivative here of this function here. So let me just extend this a little bit, okay, and start on this. Okay, so I'm going to differentiate the function. So it's going to be f prime. I'm going to set it equal to my limit as h approaches 0. F of x plus h minus f of x over h. Okay, so now I apply my function. Okay, I still need the limit as h approaches 0, but my function is telling me to square it. Okay, and I'm going to subtract the original function divided by h. Okay, so now I expand. Okay, there's no numbers here. Okay, I'm going to let x just be. I'm not going to replace x with a number, right? Like we did in the last when we evaluated limits. Okay, I'm going to work on the function, work in two variables. So work on the function, okay, and then work on this delta h. Okay, so expand x plus h. So that's x squared minus 2xh plus h squared, and then I have a minus x squared over h. Notice that, okay, the x squareds are going to cancel. Okay, so it leaves me with a limit negative 2xh plus h squared. So that's a plus. Should be a plus here. Okay. And then I factor out an h. That allows me to remove, okay, the occurrence of a 0 in the denominator. And it leaves me with an expression, the limit as h approaches 0 of 2x plus h. Okay, now I can remove my limit sign, right, when I evaluate. So when I plug in h equals 0 into this expression, I'm going to have, or just 2x. Okay, so remember that was my derivative function. Okay, and this is going to be important. My original function, okay, was x squared, and my derivative function is 2x. Okay, that's how we do this. A first principles proof in a lot of ways of a derivative. Okay, when I take the derivative of the function, I have to find the limit as h approaches 0 of the function. Okay, and that's how I find this. Okay, let's do it on the cubic function, x to the power of 3. Okay, I'm going to change my, as you guys get started on this, okay, I'm going to change my color. So I'm going to get started on it. You guys can, okay, get rolling on it. So I've got, okay, so I'm going to find, always just start with the definition. Okay, then I apply my function, and that'll be x plus h to the power 3 minus my original function. Now I have to expand. Okay, and that's just binomial expansion. 3xh squared plus h to the power 3 minus x to the power 3. Okay, notice that, okay, in all these cases, okay, the original function just cancels each other out. Okay, so I'm left with 3x squared h plus 3xh plus h to the power 3 all over h. I factor. Okay, then I can simplify, and I'm left with the limit, okay, of my expression 3x squared plus 3xh plus h squared. Okay, now I can drop my limit and put in actually h equals 0. So I'm left with 3x squared plus 3. Now, as we work on these proofs, you'll get really good at doing these, and you'll be able to drop a few steps in your solution. Okay, but in this case, I just want to write out my full solution. So there's my derivative function. Okay, my original function was a cubic. Okay, my derivative function is 3x squared. We're going to look for patterns here in a few minutes here and realize that, I mean, we've just done two, right? We've done two basic functions and its derivative. Okay, and the next one, cubic, so the basic function and its derivative. Okay, and I want you to do this one here, and I'll write this proof out here in a second. Okay, but I want you to get started on it just like we did with the last ones. Let me just pause for a second. Okay, I'm going to pick it up right here. Okay, where I've started my derivative function. I've expanded x plus h to the power 4 using just binomial expansion. Okay, and I got my coefficients here. Now the next step, as always is the case, I'm going to simplify, okay, and get rid of my x to the power 4. So that leaves me with a long expression, lots of terms here. Okay, where I'm going to factor out an h. Okay, so I can take out an h. I'm going to have 4x to the power 3 plus 6x squared h plus 4xh squared plus h to the power 3. Let me close my bracket. Divided by h. Those will cancel. I get rid of my common 0. And I'm left with and when I plug in h equals 0, that's going to neglect that one, and that one. Every place there's an h, every term where there's an h, as soon as I let h equals 0, I'm going to be left with. And it's just what we're going to notice here, the coefficient of my second term here is always this, okay, derivative function. Okay, and again, my original function was, okay, that's a good process, first principles here. I'm going to expect that you guys know how to do this. Okay, and this is, okay, the basis of finding a derivative, a polynomial, okay, on a single term here, or original function. Okay, this concept of proving a derivative, okay, or showing first principle derivative calculations. Okay, let's do it on this one. Okay, now think about this for a second. Use first principles to differentiate the function. Now this is just a real simple function, and since differentiation is the slope, okay, what's going to be the slope of this line? Okay, what is the slope of the line y equals x? Okay, my slope is 1, so that's what I should get here. Okay, so let's go with this and see here. Okay, f of x plus h minus f of x function's always the same. Now I apply my function, and that'll be x plus h minus x. Okay, notice that that just leaves me with, okay, h over h, okay, or the limit as h approaches 0 of 1, which equals 1. Okay, and that's exactly what I thought here. Okay, so when I have my original function, okay, my derivative is 1. All right, let's see what we've got. Do we see a pattern? Well, let me write down a couple of things that we did here. Okay, so the first one was x at 1, and I had a derivative of 1. When I had my function x squared, I had a derivative of 2x. When I had x to the power 3, I had 3x squared. Okay, and my derivative of x to the power 4 was 4x to the power 3. Okay, do we see a pattern? Okay, if you see a pattern, okay, we're going to put the pattern, okay, in our rule for our pattern in the box over here. Okay, I think if I see this pattern, my derivative should be, okay, of x to the power 5 should be 5x to the power 4. Okay, this one should be x to the power 0. Okay, x to the power 0 is just, okay, a constant, right? Anything to the power 0 is 1. Okay, and the derivative of, okay, constant line at 1, okay, is equal to 0. Okay, right? Okay, and then, okay, my next one, x to the negative 1, okay, would be a negative 1, and then I subtract. It looks like I subtract. It looks like my rule is I subtract. It would be a negative 2. So it would be negative 2 x to the power negative 3. And x to the power negative 3 would be, I bring my exponent down. Okay, and then I write x to the take away 1. So my rule is this. Okay, if I have a derivative, or if I have an original function, x to the power of n, let's say, then my derivative function, I bring my exponent down, and I write, get this straight, okay, I write my new power as 1 less than, okay, the original exponent. Okay, and that's really what I look for in what I saw here. Okay, does that make sense? I hope it does. Okay, that's what we were working on with those 4 examples here. Okay, so given our function, can I find f prime at 0, f prime at 1, and f prime at 2? Well, I've just found this. Okay, now normally I might use first principles here. Okay, that's the limit as h approaches 0. Okay, to find f prime at x. Okay, but I just did that proof, so I'm just going to do this. So f prime at 0, okay, would be actual value of my slope of my tangent at 0 would be, I use this function, would be 0, f prime at 1. Okay, and the point of this little example is just to show you that, okay, not only can we find a derivative function, it actually has a value. Since it's a function, it actually has values at particular points. Okay, and this is the slope of the tangent line, okay, of my original function at the point, it would be at the point x equals 0. Okay, at 1, and at 4, and at 2, when x equals 2, I have the slope of my tangent line. It'd be 32, it'd be pretty steep line here. We know, right? Okay, that cubic, or sorry, that quartic, okay, at 2, okay, has a pretty steep slope here. Okay, and that's just what I found. Okay, that's it in a nutshell. That's how we find, okay, a derivative. Oh, this is the biggest challenge here. Let's do this one here. Okay, I think we've got a couple more here, and then we're going to talk about differentiability. Okay, let's work on this one here. I'll set it up, and then I'm gonna pause it in, okay? let you do it when I... Okay, so it's going to be... Okay, and it's got conjugate, so to find it, we can multiply by the conjugate. And again, we've done these in chapter 1, so it shouldn't be a problem, it might just be a little bit of review. Okay, I'm going to pause, do it, and let you guys... Okay, so here's my derivative function, okay, of the square root function. Okay, again, we've done these before. Okay, we've multiplied by the conjugate to simplify. Okay, there's the steps. My h disappears when I factor it out, and I'm left with, okay, this final derivative function, okay, 1 over 2 root x. Now, I want to go back to my original function here, okay, and see if the power rule, this rule that we developed, actually holds true. Okay, so the square root of x, okay, as an exponent is x to the 1/2. Okay, so and if I use my rule, I bring my exponent down. To get my derivative function, I bring my exponent down, then I write my function, and I take 1 from the original exponent. Well, 1/2 take away one whole number, okay, is negative 1/2. Okay, and this derivative function will be 1 over 2, and then the negative 1/2 goes in the denominator, which is in fact what I got here. Okay, so first principles always gets me. If I'm really good at first principles always gets me the derivative. Okay, but again, so too does this rule here. Okay, let's do one more here, and then find the equation of the tangent line at the graph. Okay, this one's going to be a little bit more challenging. Okay, so I have to use first principles here, so I have to do my limit. Okay, so this will be, okay, this one's a little bit more challenging. Okay, so I'm going to take the limit as h approaches 0. Okay, and I've got 1 over x plus h squared minus 1 over x squared. Okay, and I'm just going to close, that's my numerator, and then I'm going to divide it by h. I'm just going to write it like this, okay, for a little bit more clarity here. All right. Okay, let's get a common denominator. So focus on the square brackets. I'm going to get a common denominator of x squared and then x plus h squared. Okay, and this is still going to be divided by h. Okay, so I'm going to do a couple of things in this next line here. I'm going to actually, okay, expand this. And it's all going to be over x squared and then x plus h squared. But now I'm going to divide by h, and when I divide by a fraction, I multiply by the reciprocal. Okay, that's going to allow me to bring h in here. I'm going to have times h. And in my top, I'm going to have an x squared minus x squared minus 2xh minus h squared, and that can simplify. So I'm left with limit as h approaches 0 of negative 2xh minus h squared all over x squared, x plus h squared, and then times h. Now factor. Okay. If you're paying attention, I think you might notice that all the steps when I find the limit of first principles are all the same. Okay, I write my definition, okay, I apply my function, I simplify, okay, I simplify some further, okay, and then I take out, factor out an h, get rid of my common 0, okay, and be left with my original function here, or my derivative function. Okay, those will cancel. I'm going to plug in h equals 0. I'm going to be left with negative 2x over x squared, and then an x plus 0 squared. Okay, that leaves me with 2x over x to the power 4, or negative 2x to the power 3. Okay, that's my derivative function. Can I verify that? My original function okay, was 1 over x squared. I know that to be x to the negative 2, so my derivative function using my rule would be, okay, and that's exactly what I have here. Okay, now I need to find, I'm not done this particular question yet, I've got lots more to do. I found my derivative function, so I found my slope, right? But I need it at x equals 2 here. So what's the value of my slope? Okay, that would be negative, it looks like it's negative 1/4. Okay, so do I have my point here? Do I have a point at 2 and, okay, what's my original function? Okay, it looks like if I put 2 in here, okay, so f at 2 would be, okay, 1/4, and I have a slope of negative 1/4. Again, I've done this before, my tangent line, okay, so y equals mx plus b. Okay, my point at 2, right? Okay, to find my y coordinate, I just go and plug 2 in here, this original function here. So now I can just substitute it in. So 1/4, negative 1/4, my x value is 2 plus b. That'd be negative 1/2, so plus 1/2. And I've got, okay, 3/4 equals b. So my original slope of my tangent line is negative 1/4 x plus 3/4. Okay, so that's the slope of my tangent line at the point 2 and 1/4 here. Now, if I wanted to go and confirm that in decimals, I think I will while I'm at it. Okay, and just give me a second. I'll show that in decimals here in a second. Okay, so as I suspected, my original function, my point, and my slope of my tangent line. I'm just going to zoom in. I'm going to hide this. Okay, and get rid of that. Okay, and I'm just going to zoom in here. And there's exactly my tangent line, okay, at the particular point here. Okay, all good. Okay, let's continue here. We're going to just burn through the rest of this. We have, okay, additional worksheet if you want the additional worksheet to find, using first principles to find just to practice derivatives on these functions. So I can give you that. Okay, the answers are here. So if you like, you can just practice those, finding the derivative and then comparing your answer. We need to talk a little bit about, okay, really quickly, just to finish this off, okay, continuity and differentiability. So basically, a function is continuous only if you could take the derivative of it, okay? And if there's a discontinuous point, okay, that's where we can't take the derivative. Okay, so the differentiability is to do continuity in a sense, and that's why we talked about continuity in the last chapter. Okay, and before we go and continue with, okay, understanding taking derivatives of functions, we have to respect the fact that the function has to be continuous. Okay, so if it's not continuous, it's not differentiable, and f prime at a particular point doesn't exist. Okay, so here's the different situations. Let's go back, sorry, and go back and, okay, take a look at my diagram here. Okay, so it all bases on slopes of tangent lines. So here's a continuous function, and as I move along, okay, I can always find the slope of a tangent line here. Okay, when there's a break, okay, or a change, like at a corner point, okay, look at the slope of the tangent line. Okay, look at the slope of the tangent line here, and then at the point it changes to here. So the slopes don't relate to the same values in and around that point. Same thing here, an infinite slope. Okay, so vertical tangent, and I've got a thing called a cusp line as well too. So if my function cusps to a point, okay, I have an infinite tangent slope here, and I have a problem. Now again, the other example, okay, this one here, when there's a break, look at the slope of the tangent line on the left hand side. give my discontinuity, and then the slope of my tangent line on the right hand side of my discontinuity. So if the slopes don't equal in and around that point, okay, then I can't find the derivative. Okay, so let's take a look at, okay, the following points here. Okay, so where is the function not differentiable? Okay, so I think I've done, I'm just going to go to my, okay, so here are my answers to this one. Okay, and for the reasons why here. Okay, so at the point -6, there's an infinite break. Okay, so here's my slope, and here's my slope. So the slopes, okay, at -6, there's a negative slope, and then it jumps over my -6 discontinuity point, and then my slope of my tangent line goes there. At 2, this is a corner point. Okay, here's the slope, okay, and then the slope over here. At 0, there's a jump discontinuity, so it's not differentiable. At 2, there's a cusp point, so it's not differentiable. At 4, there's a discontinuity, so it's also not differentiable. And then there's an infinite slope at 6 here. And those are all the places where it's not differentiable at these points. So we have to be aware of that as we work through, okay, this type of understanding of differentiability and continuity. Okay, there are some homework questions. Good luck with this, and we'll get going on this as well. Okay, thanks.